I'll never forget the first time that I put on a dry suit as a graduate student. And I slipped through a hole in the ice that was about 1 meter in diameter. The ice was about 6 feet deep. I was paranoid, I was claustrophobic. But as I came out the bottom of the ice for the first time, it was absolutely stunning. The seafloor below me was crystal clear. I could see 500 feet underwater. The floor was covered with sponges and soft corals and starfish and sea urchins as far as I could see. For 10 years, I lived and worked and visited McMurdo Station, the largest of the American stations. About 1,000 Americans during the summer, maybe about 200 in the winter. It was a fantastic place to do research in marine ecology. But every now and then I'd go into the cafeteria and somebody would say to me, "Have you ever heard of Palmer Station?" And I'd say, "Well, yeah, I guess I have." It's this little station, about 40 people. It's perched up on the Antarctic Peninsula below South America. We call it the Banana Belt. And it's really a beautiful station. And I always thought, how cool would it be to get to work and do research at Palmer Station? Well, my area of chemical ecology took me to Palmer Station because it turns out there's lots of seaweeds there and there aren't any at McMurdo, and they chemically defend themselves. So we have spent, Chuck Amser, who's on campus with me here, and I have now spent the last 20 years running, funded by the NSF, working on chemical ecology at Palmer Station, and more recently on climate change and ocean acidification. Well, I got to Palmer Station, and I had no idea that I was moving to one of the most rapidly changing regions of the planet. And that's really the narrative that I want to share with you today, is what's going on this 800-mile stretch of the peninsula. So if you go back to National Geographic, and this is back in 2006, you can see that there was sort of this Arctic-centric way of looking at warming. Actually, scientists hadn't really parsed the data real carefully for Antarctica. And in a more prestigious journal that we call Nature, on the cover of Nature, when scientists really began to look at the satellite data and the station data for Antarctica, it wasn't just the peninsula that was warming, but the western side of the continent as well. Now you have to realize that you're looking at a continent the size of India and China combined. This is a very big place. It's exactly the opposite of the Arctic. Remember, the Arctic is an ocean surrounded by continents. Antarctica is a continent surrounded by oceans. So, we also know now that it's not all to the west, but because we can look at ice sheets, or ice shelves, I should say, that are melting around the continent, we now know that even over on the eastern side of the continent, some of the ice shelves are losing mass. Now, ice shelves, for those of you that don't know, are about 1,000-foot thick ice that is attached to the land. Okay? And we'll talk more about those in a minute. So how much warming are we talking about along the western peninsula? Well, how cool is it that the station 20 miles from us, our neighbor, used to be British, but they sold it to the Ukrainians, that's right, for $1 or £1, I think it was. The Ukrainians have had it for a number of years, but the beauty of this station is that for over 60 years, air temperatures have been taken daily. And if you plot those temperatures over that period of time, the temperature has increased about 10 degrees Fahrenheit in 60 years. So that's a degree centigrade per decade. So this makes this region of the world one of the most rapidly warming regions, perhaps even more aggressive than what you hear about in the Arctic. So what does it mean? Well, it means that when I arrived at Palmer Station 20 years ago, about once a week I'd be sitting at my computer and I'd hear a huge crash. And I'd leap up and I'd run down the hall with my colleagues. We'd open the door and look out into the bay, and there would be a huge wave coming down the bay because the Mar Glacier behind the station had just dropped a chunk of ice into the water the size of a couple of houses. This was a big deal. When I was at Palmer a year and a half ago, this was happening 2 or 3 times a day. The backdrop of the sound of the ice cracking was part of the norm. We're literally in that period of time. 87% of the glaciers along the western Antarctic Peninsula are in recession at this time. Now we have more quantitative data than running down halls. You can actually measure the retreat of the glacier. And every several years, I coax the science technician at the station to put on a backpack. And she did this in 2017, most recently, and told her to go hike the glacier. So she spent the whole day hiking the leading edge of the glacier with a GPS in her backpack, talking to a satellite above her that was marking her position at an accuracy of about 1 centimeter, and then she'd come back and add a line. And she'd add a line to the map that shows where the glacier has been going. You can see the 2017 line. Here's where Dr. Amsler and Maggie Amsler, our colleagues over across the road here in Campbell Hall, used to come down to the station back in the old days in the 70s when they said you could open the door of the station and almost step onto the glacier. And now it's about a ½ kilometer hike. You can see it in these aerial images. You can see where the edge of the Mar Glacier was in 1975 compared to 2013. It's quite dramatic. And so we have a lot of glaciers that are retreating. We also can now, and how cool is this, have technology that measures glacial thinning. Satellite-mounted equipment that can measure thinning of glaciers to an accuracy of about 1 centimeter. And you can see areas of melt mostly on the west, the peninsula, a little bit over on the east, and look at Greenland. Now, whoever decided to name Greenland, Greenland, and Iceland, Iceland, I have no idea what they were thinking, because the one that has the ice is Greenland, and the one that doesn't have the ice is Iceland. But anyway, Greenland has a big ice sheet sitting on top of it that's melting as we sit here very rapidly. This was a surprise. Scientists were caught off guard about the Thwaites Glacier. The Thwaites Glacier is on the western side of the continent. We knew it was receding. It's just that scientists didn't realize how fast it's receding. Look at this, 14 kilometers between 92 and 2011. That's an amazing rate of retreat. So the concern about it is not so much the rate of retreat, but the fact that it's a figurative cork. The Thwaites Glacier is the point at which the ice sitting on top of Antarctica is moving seaward. All right, now I haven't mentioned the ice on top of Antarctica. There is a 2 to 3 mile thick chunk of ice sitting on top of a continent the size of India and China. There is 70% of the Earth's fresh water locked into that ice. This is a big piece of ice. That ice is not stationary. On the western side of the continent, the ice sheet moves towards the west, and on the east to the east, and on the west it funnels down through where the Thwaites Glacier is. The concern with the Thwaites Glacier disappearing is the rate of ice flow of that ice sheet could be accelerated, which would mean that sea level rise could be much more than we would want to be dealing with, because ice that comes from land that enters water contributes to sea level rise. So ice sheets. I already told you ice sheets are about 1,000 feet thick. They're attached to land. Let's look what's been happening to some of the ice sheets around the peninsula. So this ice sheet over on the east side, the Larsen B ice shelf, was imaged by a satellite in 2002. And the scientists that looked at the image said, whoa, there are some striations in that ice sheet. What's happening? Let's go back and look a month later. And they went back a month later, and the Larsen B ice shelf was collapsing. And 2 weeks later, it did. The Larsen B ice shelf went out to sea. A chunk of ice the size of the state of Rhode Island floated out. Okay? It's a big event. More recently, you might have heard about the Larsen C ice shelf. Now, this was in all the news about 2 years ago. And the first thing that was noticed was a big crack in the Larsen C ice. And they'd go back and look at the crack, and they'd see it was widening. And eventually, that thing floated out to sea. When it floated out to sea, it was in the top 10 of the largest icebergs ever recorded in humanity's history. It was an iceberg the size of the state of Delaware. Okay? Now, the good thing about these events is that ice sheets, when they break up and melt, do not contribute to sea level rise. The reason for that is because that ice is already in the ocean. Okay? It's the same physics as a glass of ice water. When the ice melts, you don't see the water come over the top of the glass. Okay? So that's good. The concerning news is that these ice shelves serve as barriers to the ice sheet that's moving off the continent. So you take away the ice shelf, and the rate of flow of ice from the continent is accelerated up to 4 times. And that contributes to sea level rise, and that's why the IPCC has taken Antarctica into account in estimating by this century's end up to about a meter of sea level rise. That's a guess. Anywhere from a half a meter to a meter of sea level rise. That's not a big deal if you're in Birmingham. It's a really big deal if you're in Miami, right? Okay. So those are some of the things that are happening with the ice. What is happening to the marine communities in this very rapidly changing area? And that's what's interesting to me because I'm a marine ecologist and I've been studying Antarctic marine systems for a very long time. And I was curious what's going on, as are many scientists now working in Antarctica. Probably the most poignant story that I can share with you today is the story of the Adelie penguin. And this is a group of penguins that look like Charlie Chaplin. They wear little tuxedos. And in front of our station, there has been a colony of Adelie penguins for a very long time. In fact, the gentleman in the backdrop of this image, a good friend of mine, Bill Fraser, arrived at Palmer Station 46 years ago as a graduate student. And for his doctoral dissertation, he tagged 16,000 breeding pairs of Adelie penguins. That is a dissertation. Now, Bill has come back every year for 45 or 46 years, and he has followed the fate of that population of penguins. Sadly, what's happening to Bill's penguins is not good news. The purple line is for the Adelie, and you can see on the left when he labeled 16,000 or tagged 16,000 pairs in 1974, and he told me in an email about a month ago that the final count this year is 1,100. So we're down about 90%. Sadly, the Adelies are not moving because they never find a tagged Adelie in another rookery. They're disappearing. Now, interestingly, at the same time, in the 1970s, a small number of chinstrap penguins, the one up in the top right, showed up. And notice the axis is very different on the right. There's only a few hundred of these. But then in the 90s, the gentoo penguin, the one in the middle, the largest of the 3 brush-tailed penguins, showed up, and there's now over 1,000 breeding pairs of gentoo penguins. Well, what's interesting is that these penguins kind of shouldn't be here. They're warmer weather species that live further up the peninsula, but as the peninsula is warming to the south, they're beginning to move in. So they are extending their range and sort of taking over, if you will. So, what in the world is happening to Bill's penguins? Well, one of the things that's happening is that as the air is warming on the peninsula, it's getting more humid. And with humidity comes snowfall. And snowfall later than it used to come. So what happens is that the Adelies are genetically programmed to show up at about the same time, even week, every year. They lay all their eggs, and then along comes an unseasonably late snowstorm, buries the entire colony, and sadly, when the snow melts, the eggs effectively drown. So you can lose an entire generation of these penguins in these increasingly common snow events. The other thing is that the sea ice is disappearing. Now, I haven't mentioned sea ice to you yet. Sea ice is only about 5 feet deep, but it doubles the size of Antarctica in the winter and then goes away in the summer every year in a very predictable way. It's so predictable that a lot of the marine organisms sort of have tied their ecology to the sea ice. They're sea ice dependent species. And the Adelie penguin is one of those. In the context that they use the platform of sea ice to toboggan across. They get down on their bellies, you might have seen this, and they glide along, and they can get out to the ice edge and then get in the water and feed on schools of krill. And krill are shrimp-like organisms that are the quintessential base of the food webs of Antarctica. So what's happening now is the penguins, the Adelies, have to get into the ocean much sooner than they used to. And they have to swim much further to their food source. And Bill thinks that they're on such a tight energy budget to raise their offspring that that's hurting the success of their offspring. And then the krill, the actual krill themselves, we have discovered in the last 20 years, are also dependent upon sea ice. It turns out that when krill are teenagers, they live underneath the sea ice, feeding on diatoms, little tiny plant cells that turn the underside of the ice green. So as that sea ice is depleted along the coast of the peninsula, there's a possibility that the krill populations are going to be impacted by the loss of this habitat and this food source tied to their life history. Any of the organisms that feed on krill could be impacted. For example, the baleen whales, these beautiful humpback whales. Now the good news I can share with you today is that whales in Antarctica are doing quite well. They are actually thought to be at the point of recovery from whaling. Now you may be aware that whaling was quite aggressive in Antarctica, and it has taken a long time, but the whale biologists that I've spoken with say that they think that populations are beginning to take off again. And I can testify to that. The last cruise I went on to Antarctica, I counted 76 humpback whales in one afternoon. Wow. And if you're really lucky, if you come on the cruise that I lead to Antarctica, you can watch bubble feeding. So bubble feeding is awesome. It's when humpback whales take big breaths of air and they dive down about 50 feet and they blow a concentric cylinder of bubbles. And what that does is it scares the krill together into a ball within the bubble cylinder. And then the whales have some fun. They go down and they come lunging up through the cylinder of bubbles and out of the ocean, and you can see the krill sieve being kind of pulled off of the baleen sieve and right there below you on the ship. It's just absolutely spectacular. So it's a feeding tactic to feed on krill. What else might be affected by the loss of the sea ice? Well, this is a sea ice dependent species, the Antarctic Weddell seal. Beautiful seal, my favorite. And this seal has a remarkable adaptation. The female has ice chipping teeth. And what she does is when she's pregnant, she goes up under the sea ice and looks for a weak spot, and she'll start chipping at it until she has a little breathing hole, and then she'll enlarge that hole with her teeth until it's large enough that she can slide right up through the hole and give birth next to the hole. Her pup's completely safe from the killer whales and the leopard seals that are prowling the ice edge, and all because of her dentition. It's really cool. Now, I don't think these seals will necessarily disappear like the adelies are. I think they'll follow the sea ice, but nobody really knows the answer. Nobody knows what's going to happen to the leopard seal, the top of the food web, 10 feet long, 1,000 pounds. When we see a leopard seal and we're diving, if you're in the boat, you're tending the divers, you drop a siren into the water and you set it off. Yeah. And the divers hear the siren immediately. They come together back to back. By now, the leopard seal is probably making passes by the divers. And when the divers see the leopard seal go off a little distance, they come real quick and we pull them into the boat and we leave that area to the leopard seal because they are top predators. They've never been known to prey on people as food, but because we're scientists, we do not want to test that hypothesis. Right? Now, these are beautiful animals. And when you go on the Zodiac, you can cut up to an ice floe and look at them 10 feet from you. These animals have never been seen, ever, giving birth anywhere except on an ice floe. So nobody knows what's going to happen when the ice is gone. Are they going to go to shore and give birth, or are they going to follow the ice? It's just a question. What about the tiny things in the ocean in Antarctica? What about the plankton? You know, there's phytoplankton that photosynthesizes and provides energy for zooplankton. What's going to happen under these very dramatic changing conditions? Well, the guy with the white cap here was Hugh Ducklow, was giving a seminar this past Monday here. He's a professor at Columbia, all of his degrees from Harvard, and he has been the director of the LTER program for the last 15 years. So this is a program that stands for Long-Term Ecological Research. It's an NSF-funded program with about 10 different PIs. maybe 20 more investigators involved. And for 35 years, they've been going to Antarctica with a ship and running transects up and down the western part of the peninsula. 35 years, sampling all these stations for phytoplankton, for zooplankton, for water chemistry, for physics, you name it. The data is absolutely astoundingly abundant. So I asked you to put it in one slide. You did a pretty good job. So in the big picture, we're going from a polar, dry climate to a much warmer, humid, sort of sub-Antarctic climate. If you look at the top two cartoons, you're looking at the tip of the peninsula, and you're comparing the 70s and 80s with the 90s and 2000s. And what you see happening there is pretty remarkable. We're changing the weather with this. We're getting cloudier days. It's windier. The winds are churning up the surface of the ocean and pushing the phytoplankton deeper, where some of the species of phytoplankton that the krill really like to eat are having a tough time. They're disappearing. So the krill are kind of going down in numbers, and instead of krill, we have salps. Now, salps are not really good news for a food web. Salps are tunicates. They're the size of a walnut. They look like jello, gelatinous organisms. Believe it or not, we're related to them. Salps are lettuce. Krill are steak. And that's what we're kind of having a problem changing those out. Now, further down the peninsula, in the bottom two cartoons, Hugh says that things haven't changed as much, but he thinks in a few decades it's going to look a lot like the northern part of the peninsula. So big changes in the plankton. What's happening to the forests? That's right. You didn't know that there are forests in Antarctica. All you have to do to find the forest is put on your dry suit, throw on a tank, and swim with me out in front of the station. We will be swimming in a forest of seaweeds. Some of them will be 30 feet over your head with blades 10 feet long. There are 150 species of seaweeds on the western Antarctic Peninsula. Now, I think these forests in a warming world are going to do pretty well because that sea ice above them isn't going to be there anymore. So they're going to have more light, and they'll probably extend down into deeper water or further down the peninsula. But we also know from our own research that these seaweeds are loaded with chemical defenses. And that's because they live in a soup of predators, little crustaceans that want to eat them. What's going to happen with more light is they're going to have more energy. With more energy, they might produce more chemistry or different chemistry. Or we don't know how that's going to affect the trophic food web. Who eats who? That could be a problem. What about the offspring of starfish and sea urchins? Sponges, corals. They're called larvae. Larvae are the babies. Larvae is fundamentally different from the adult as a caterpillar is from a butterfly. A lot of people here probably wouldn't realize they're looking at a sea star in this picture. And this little larval sea star will spend 4 months developing in the water in Antarctica, which is a very long time. And we know from studies that have brought these larvae into the laboratory and warmed the temperature just 2 degrees centigrade, that they don't necessarily die, but they develop a lot faster, maybe twice as fast, or even more. That could be good with warming. Maybe that means they're in the water for less time to be eaten by predators. Or it could be a problem because a lot of these larvae feed. They feed on phytoplankton. Phytoplankton bloom at a particular time. What if they show up at the cafeteria and the door's locked? And that's something that climate scientists worry about in many systems, the displacement of predator from prey. What other species are showing up that haven't been around much before? Well, I already told you the Gen 2 penguin and the chinstrap are moving down. Elephant seals arrived. Elephant seals tend to be up in warmer places. They now have established a breeding colony. They're having pups near the station. You can hear them barking. On a warm summer day, you can have 10 big 2,000-pound elephant seals laying in the middle of the station. Do you know what that smells like? It is wicked. The other seal that's moved in is the one in the bottom image. That's the Antarctic fur seal. which was almost hunted to extinction for its beautiful pelt. It's a wonderful story of recovery. There are now hundreds and hundreds of thousands of pursuits again. They have arrived. They haven't established a breeding colony, but they are extending their range into this area as it's warming. Probably the most poignant example I can give you today of a range extension, or maybe even an invasion. I'll set the stage with this slide. You are looking at the ancient seafloor community of Antarctica. Ancient in the sense that Antarctica separated from South America 40 million years ago on its way to that position at the South Pole. When that happened, it allowed the establishment of the Antarctic Circumpolar Current, the largest current on our planet, and it goes in a clockwise direction around Antarctica. Hugely important current for many reasons. But at that time in our history, it essentially locked Antarctica into a deep freeze. So the species that could adapt to the cold did, and a number did not. There are some very conspicuous things that are not found in Antarctica. There are no sharks in Antarctic waters. There are no durophagous fish. That just means fish that are capable of crushing things with their jaws. All 250 species of Antarctic fish are wimps. They have little jaws. They eat little crustaceans. There is nothing in the Antarctic Ocean that has a claw. There are no crabs. There are no lobsters. In other words, there is nothing that can crush a clam. So if I was to hand Dean Irwin an Antarctic clam, he could take 2 fingers and he could just crush it. The shells are very weakly calcified, probably because they've never had to deal with crushing predators. If you go down to Gulf shores, you'll pick up a pretty robust looking snail shell or clam shell, and that's because there's so many things that want to crunch that. So, given that backdrop, you can imagine the shock of my colleague Sven Thatchy, who on, I forget the date of it, but it's about 10 years ago, was flying a remotely operated submarine up the slope of Antarctica towards the shelf, and for the first time ever, 13 king crabs were discovered on the slope of Antarctica. Now, why is this a surprise to biologists? It's a surprise because while we know that king crabs have lived in the deep sea around Antarctica for a very long time, the thought was that as you climb the slope, it actually gets colder. And king crabs do not do well at cold temperatures. They act like they're drunk. They fall over. They can't find their mouths. They miss it. And it's because they can't regulate magnesium in their blood. It's a narcotic. And so this was the theory. So maybe the proverbial curtains are being opened in a physiological sense. And these crabs are beginning their climb. Now, we put a grant proposal in, a colleague at the University of, actually at FIT, Rich Aronson and I, to the NSF to study these populations and see how many were on the slope, have they gotten to the shelf, what are they eating, are they reproductive? And while we waited for our proposal to get reviewed, another group of scientists just bumbled into 1.5 million king crabs in a deep canyon within sight of our station at Palmer. Now the canyon is deep. It's actually below the level of the slope. But it just goes to show they're poised. So we got our funding, and we've done this now. We've got 2 rounds of funding. We've been to Antarctica with the ship 3 times. And what we do is we take the ship down to the Antarctic Peninsula, and we lease a submarine from Woods Hole, and we tow the submarine up the Antarctic slope and onto the shelf in 10-kilometer long transects at various sites along the peninsula. On the submarine are cameras, and they're taking images of the seafloor every 15 seconds. So you can imagine how many images we have from 3 cruises. And when you have a tremendous database like that, you use a very technical research tool to analyze the data. It's called the graduate student. We have lots of graduate students that have analyzed all these images, and the bottom line is there are king crabs on the slope in the millions. They are feeding on things and changing the ecology. They have not reached the shelf, so they're a couple hundred meters below the shelf. So that's good. We hope they don't, and we hope to go back and continue to follow that. Lastly, but not least, ocean acidification. Now, this is something that's happening to all the world's oceans and does not get the press it deserves. It's sort of the lonely stepchild to climate warming. Since the Industrial Revolution, about 30% of the carbon dioxide that's been released from burning fossil fuels has found its way into the world's oceans because oceans absorb CO2. That means that since the Industrial Revolution, the world's oceans have become, on average, about 30% more acidic than they used to be. This is a challenge if you make a shell, because your shell will dissolve. Doesn't mean that it's going to go away. It does mean that you'll have to use more energy to keep your shell intact. So there are consequences of this. Antarctica is the canary in the coal mine for ocean acidification for several reasons. One of them you already know. Things are very weakly calcified to begin with. The other is that the colder the ocean is, the more CO2 is absorbed. Basic physics property. So the Southern Ocean is the most acidic, if you will, of any ocean. So we have had some funding from NSF to send UAB graduate students down and study ocean acidification at Palmer Station. Now, one of the things that when you think about this is that we're not talking necessarily about the future. You can go to the Southern Ocean today and you can take a net and dip up one of these beautiful little sea butterflies. It's a snail that has lost its foot and evolved wings, and it flaps in the water. Sometimes they're called sea angels. They're the size of the tip of a pencil, but as common as the stars in the sky. They are so abundant that they're part of the global carbon cycle of the planet. Right? You can dip them out of the Southern Ocean, put them under a microscope, and you can see on the aragonite shell etching from ocean acidification. In other words, they're already showing some effects of ocean acidification on dissolving that beautiful shell. So we had this program at Palmer Station. We've looked at a number of different species and how they respond to ocean acidification. These two scientists that work in our lab spent 2 very long seasons at Palmer Station, 6 months, twice. And you would think, oh my God, those poor students. Actually, we have a really hard time getting our UAB students out of Palmer Station. They do not want to leave the station. It's a beautiful place to work, exciting science, 2 chefs. I mean, think about that. Are a graduate student. Anyway, they have published between the two of them about 15 papers now on the impacts of ocean acidification. One of the things they found was that amphipods, these little shrimp-like animals, are susceptible to ocean acidification. Not all of them, but some of them are very sensitive. So we're going to be going back this spring to continue looking at that question, and also at the community level. But I wanted to just sort of divert you to a little story of discovery that's in this image. And it just goes to show how Antarctica is still such an amazingly sort of foreign, exotic place to visit. So one day I was out on the sea ice and I looked down in the ice hole and I saw a little amphipod swimming by carrying an orange backpack. And I thought, this is really odd. So I got a little net and I put it in a bucket and I took it up to the lab and I showed John Jansen, who was a fish biologist, and he and I worked together over the next several months, teasing apart what was going on. And the first thing we did was to tease off the little orange backpack, which opened its wings and flew away. It was a sea butterfly. It belonged to a different group of sea butterflies that don't have shells. They're called naked sea butterflies. We put nets all around the sound, and we caught hundreds of these amphipods, and a significant number of them were each carrying an orange backpack. Why would they go to all the trouble of abducting another species and carrying it on their back? So we brought them in the lab, and we took the little orange backpacks off, and we offered the amphipods to fish. And the fish predators would eat them every time. They loved amphipods. But if you left the little sea butterfly on the back of the amphipod and gave it to a fish, they'd take it in their mouth and then they'd spit it right back out. Because we discovered that there is a nasty chemical in that sea butterfly that tastes absolutely terrible if you're a fish. We named it pteroenone. So this is a very smart amphipod. It figured out how to abduct another species, carry it around for its own defense. And it was such a rare discovery that it actually was published in Nature, which is really a neat place to have it published. So neat discoveries are still possible in Antarctica. So this is a laundry list of what I've just told you. How the ice is changing, the glaciers, the ice sheets, organisms that are extending their range, phytoplankton, zooplankton changing, species showing up that hadn't been there before. We might even have king crabs in that system, and ocean acidification. We're going from a system that has looked like this for millennia. We have had very dependable seasonal sea ice. The Adelie penguin has been the dominant species. The other penguins have not been part of the picture. The seafloor communities being fed by that Antarctic circumpolar current, the ACC, which is very nutrient-rich water, a fair number of krill. And now we're going to a community that'll look like this. Probably by mid-century, the ice is going to be gone. With it, the Adelie, and we'll probably have the chinstrap and the gentoo living there. We might have king crabs. The forests will have expanded, and again, all being fed by this Antarctic circumpolar current, and not very much in the way of krill. So, you're thinking, communities always change. Well, that's the deal here. So that's the deal when you think about climate change. It's the rate of change. It's not the change per se, because communities have always changed. That's natural. That's ecology, right? But what's happening now? When people ask you, what's the big deal? It's the rate of change. Because organisms that have adapted to these communities don't have the capacity necessarily to make such rapid change themselves. And that we're going to have a lot of species going extinct, as you've well read. So, who cares? It's a long way from the School of Public Health to Antarctica. We could leave right now. We'd have to fly, probably to either Santiago or Buenos Aires, and then down to the peninsula, down to the tip of the peninsula of South America, or the point down there, Cape Horn. And then we'd have to get on a ship, because you can't fly to Palmer. It'd take 4 days to get. It'd take a week if we left right now. So out of sight, out of mind, why bother telling you about all this? Well, let me give you a wonderful example of something that's very important, particularly to you in this room. And that is that when we do our chemical ecology research, which is funded by the National Science Foundation, they have a section of their grants that are known as broader impacts. They love it when you do something where you're amplifying the impact of your work. So what's a natural a chemical ecology thing to do? Well, when we discover chemicals that are important for ecological reasons, why not use the drug discovery chemist as part of our team to see if these chemicals might have activity against cancer and AIDS and cystic fibrosis and bacterial infections and on down the line. So we've been doing this for 30 years. And what's really cool is we've actually found some pretty cool stuff. When we're diving, we're collecting extra material so we can extract more to make crude extracts and to find chemicals. So let me just tell you about 2 examples. This is a tunicate that's in front of Palmer Station. It coats the seafloor. It's orange, and it's about the size of a baseball, these little blobs. So we collected this tunicate, and we sent it off to the National Cancer Institute, and they screened it against 20 different types of human cancer cell lines, and they called us up. And they said, this chemical that you've named after the station, palmerolide, we really are excited about it. It's very potent against only one type of cancer. It doesn't have any activity against the other 19. Can we work on it? Because we love to see specificity, we love to see potency, and when the NCI asks you if they can work on your chemical, you say, sure, you can work on it. And so they took their scientists and they put them to work, and the first thing they did was to be able to produce it in the laboratory. You cannot go to Antarctica with giant barges and harvest thousands of kilograms of this thing and try to get back across the roughest seas in the world, right? So you have to be able to make it a drug candidate. So they did. It was complicated, took 13 steps, but they made palmerolide. Then they took it and they put a radio tag on it, and they did some experiment with mice where they test to see if it's deliverable. Does the chemical move through tissues and membranes and get to the cancer cells that they had planted in the mouse? And the answer was yes. And excitingly, since that has all happened, we got a grant from the NIH, or my chemist did, and now the gene that produces palmarolite has been sequenced, and you could take the gene and stick it in E. coli and tell it to make the chemical, which you don't have to do the 13 steps. So drug company might really like that. So my point here is that someday we could have a drug to fight melanoma skin cancer that comes from Antarctica. How cool would that be? And there's not a lot of drugs to fight melanoma. Maybe even more exciting was this discovery. And I was recently, maybe a year ago, I was invited down to do a grand rounds talk in surgery because of this chemical in the med school here. So this is a chemical that comes from an Antarctic sponge called Dendrilla membranosa. And it's a chemical that's very potent against MRSA. MRSA in the form of a biofilm. In other words, it's under a biofilm. And the excitement was that no chemical to date had ever had efficacy against MRSA, this infection you get now when you go to the hospital that can be very deadly, under a biofilm. So something about this chemical might yield information about the mechanism to get under that biofilm. It's a big problem for surgeons because they put in an artificial knee, and then they get the biofilm of the MRSA, they have to take out their implant, clear the patient, and do the second surgery. So this is very exciting. So what is the point? The point is we have 40 million years of chemical evolution that's occurred in a very rich community of Antarctica on the seafloor. Why would we squander the potential that that has for humankind in the future in terms of medicine because of climate? I think that that's something to think about. Now, I used to get asked this question as I travel around the country talking about climate. I have not been asked this question probably in 5 years. Most people now believe that on average, the Earth is warming. So I encourage you to go online and Google global warming and find your data that will show you the thing that's happening that we all know. But I wanted to share with you the data that definitely convinced me. This is hard data that nobody can take any. I just think that this is priceless. So the question now that I get is, okay, so everybody, for the most part everybody, knows it's warming. Do we have anything to do with it, or is this some kind of a natural cycle? You know, these things cycle through all the time. Things are always changing, right? So I want to show you the data that convinced me, a scientist, that we are indeed largely responsible for what's happening in terms of warming. All right, and how perfect. The data's from Antarctica. And what you're looking at in this image is an ice core. Okay, and the ice core is laying on its side. And the bottom of the ice core is about the diameter of a grapefruit. And this ice core goes down 3,600 meters through the ice sheet of Antarctica. So on the left-hand bottom side of that ice core, we're back 420,000 years from now, because that's how old the ice is at the base of that core. And what's so neat about this ice core is that as it comes up, there are little air bubbles trapped in the ice core. And in those air bubbles is a historic record of the atmosphere at the time that the ice was formed. So we have a historic record of the atmosphere, and because we can analyze CO2 in the red line from those air bubbles, we know the level of CO2 over the last 420,000 years because of Antarctic ice. That is so cool. And think about it, they've taken it back now to 1.5 million years with the same pattern. Look at the greenhouse gas. Look at the red line. The blue line is temperature, which is an indirect measurement. Look at that red line over the last 420,000 years. I put a big black line across the top to show you at no time has it ever been more than 300 parts per million. Look what happens to it when you go over on the right-hand side and we get to the Industrial Revolution. The level of CO2 just skyrockets when we start burning fossil fuel. In fact, this is dated. The latest measurement was 411 parts per million. So we've got more than a 25% increase in a very well-established greenhouse gas, a warming gas, that is attributable to our burning fossil fuel. So I can't tell you if we're 60% responsible for what's going on or 80. but I do believe it's significant. It's really significant. Now, you wanted to know why those red lines go up and down in that 100,000-year period, because you're all scientists and you're very curious about these things. Well, that's called the Milankovitch cycle. It's a 100,000-year elliptical orbit of the Earth around the sun. And if you think about it, this gives you some sense of what the Earth should be doing right now, which is actually cooling, which is more evidence that we're having an impact. So, is this all in Antarctica? Is all I've been talking about going to stay in Antarctica? And I just wanted to bring it home for you, because here in Alabama, there are impacts of climate change that are related to Antarctica. I know it seems crazy, it's so far away, but that giant current that I talked about, the global circulatory current, the Antarctic circumpolar current, is part of what they call the Great Ocean Conveyor Belt. And what happens in those current systems that are being impacted by warming have influence on both the Atlantic and Pacific currents that influence our climate, even here in North America. So Antarctica does have a role in our changing climate. The other thing, of course, is ice, and I'll talk about that in a minute. So this map came out very recently, and it shows areas of North America that are warming. When I first looked at it, I was gleeful. I thought, oh my goodness, the South is doing such a good job. Why aren't we warming like the rest of the country? We had too much air pollution. The particulates were blocking the warming. And now that the air is actually cleared up a little bit, we're going to catch up with everybody else in the country. Oh, rats. What about numbers of hot days, as we have 101 index for the 100th day? So, I don't know about you guys, and I'm not a weatherman, but typically what's happening now is we're having hotter days than we used to, and hotter nights too, and that's an important thing as well. It's not cooling down. This is a problem for, of course, health, human health. It's a problem for biological systems. It's just a big problem all over. And I just wrote an op-ed that's being looked at by the New York Times as I stand here that relates climate change to college football in the South. And, you know, I picked up the newspaper, and the medical director at Bryant-Denton Stadium was flabbergasted. They'd had 100 medical people on staff for the Ole Miss game. It wasn't near enough. They were treating people for heat stroke throughout the stadium. Saban wants to move the games. Somebody needs to get him to mention climate change. Hotter days. With more heat, we have a warmer ocean. Now, I don't know about you guys, but last year, I thought it was unusual to have 3 Category 5 storms come across the Atlantic. And what they're doing is they're coming across at 2s and 3s, but then they get to that supercharged warm water, and they heat up before they hit us. And the one that came across Mexico Beach, which is this one, right? This is an image here, I think, of it, Mexico Beach. I drove through there after it was just looked like an apocalypse. That was later reclassified as a 5. We're not necessarily having more hurricanes with climate change, but we're having more intense hurricanes. And that's a big deal because they do a lot more damage. The Antarctic ice sheet is melting, and that's contributing to sea level rise. Now, you can go and look at maps from the past. This is 60 to 2011. We're actually in an area that has pretty aggressive sea level rise, as it is. And this sounds like a few inches shouldn't make a difference, but it does. And it means when we have storms, the surge comes in more. We do not have high tide flooding of our streets like Miami does now. You know that on king tides in Miami, there are streets with seawater. And there are people now asking, is my beach condo far enough from the beach instead of am I on the beach in Miami? Which, if you think about the real estate implications, is quite profound. You can go to Dauphin Island, and you can drive down to the west end of Dauphin Island here in Alabama and see the effects of sea level rise. There are houses now that are becoming one with the ocean. We're having heavier rain. I think I can say that definitively. When it rains now in Alabama, it comes down harder and more torrential than it used to. And that means that we don't get more inches of rain necessarily over the year, but when we do have rain, it can be very damaging, flooding, The Cahaba River, my beloved Cahaba River, is filled with chocolatey water. It's ripping out the banks because the river is so high and powerful. So these are implications as well. So, gloom and doom. But I'm going to leave you with a nice, hopeful story, okay? As I really believe that there is some. And how cool, again, is it that this is in Antarctica? It just happens to be in Antarctica that two technicians were sitting at their desk in 1985. They looked at the data and said, there is no way our boss in England is going to believe the data. He did not. He said, you're going back to Antarctica. I'm getting you a new spectrophotometer. You're going back next year. You got to do it all over again. But they found the same thing. And they published in Nature probably the most important paper of the 20th century, announcing a massive hole in the ozone over the entire continent of Antarctica. That critical layer of our atmosphere that protects us from ultraviolet radiation was missing. The hole was so big that when I lived in New Zealand 15 years ago on sabbatical, it actually drifted over New Zealand sometimes. And I could tell when it was there because in the newspaper, it would tell you what level of sunscreen to put on that day as a function of the hole in the ozone. And New Zealand has the highest rates of skin cancer, so they were really concerned about this. It's a big deal. What was so amazing, though, was that 2 years after the paper in Nature, 1987, 20 countries sat down around a table in Montreal, Canada, and ratified the Montreal Protocol that regulated the chlorofluorocarbons, the refrigerants that were destroying our ozone. Today, there are 197 signatories to that treaty. It is by far the most successful treaty of all time. Really. And it's worked. Guess what? Susan Solomon, the scientist at MIT who discovered how the chemistry works for the destruction of the ozone, told me that now they think it's going away mid-century instead of end of century. The hole is closing. And guess what? The companies that produce the refrigerants didn't go out of business. They didn't lose jobs. They used technology to come up with other ways of producing refrigerants that did not destroy the ozone. So I offer this to you as a model of what we could do. It's a bigger challenge with CO2, but it's certainly solvable. We have the technology to address this problem. So I'm going to end very quickly with just telling you about my outreach. Why is a UAB scientist running around the country talking about climate change, and how do you get the general public to do something about it? Well, you have to write a book. A lot of you brought the book. I'll sign your books if I have it afterwards. To write a book, you have to have what is called a literary agent. In order to have a literary agent, you have to have a book. So this was the problem. If you don't have the literary agent, you have to know somebody. And so I knew somebody. I knew somebody that's dear to all of us in Alabama, E.O. Wilson, who I nominated for the Ireland Award here when I was a lowly assistant professor, not knowing that when he won it, I had to take him around all week. I was his grunt. I had to pick him up at the hotel. I had to take him to lunch with the dean of medicine. It was a long week, but by the end of the week, E.O. Wilson and I were friends. And he took me on, and he has been my mentor for 20 years. So he got me a literary agent, and my book came out, Lost Antarctica, and the director of the E.O. Wilson Biodiversity Foundation called me and said, Jim, we're going to put you on the advisory board, and we love the chapter about the Adelie penguin. We want to make a video, a 3-minute video based on your chapter that's going to go in all the zoos and aquariums of America. It's going to be wonderful. I love the prose, and I thought she was asking me to narrate it. And she said, no, we'll have Harrison do it. Who the heck is Harrison? Well, Harrison Ford, he's on the committee. He said he's on the advisory board with you. I said, oh, so you can go to this wonderful YouTube and listen to Harrison Ford reading from my book. He did a very good job. He took this very seriously. I was very proud to have him do that. The other thing that happened related to the book was this. So who would have thought that I was minding my own business as the scientist at the station one day, and I was asked by the station director if I would host some guests for the next day, a visit, and tell them about the science. And I said, of course I will. Who is it? And he said, I can't tell you. And I said, why? And he said, security. I said, but we're in Antarctica. So the next day, Bill Gates and his father, Bill Sr. came, and his mother, Bill's stepmother, and his son Rory, who was about 10 at the time. And I showed them all around, and I talked about the science, and they visited the different scientists. And Bill wanted to know all about climate change, and he told us about his work in healthcare in Africa, and it was really neat. He asked me if I had enough money, and I blew it and said yes. Well, he was asking if NSF took care of us down there. And I don't know why. They take care of us. But I should have asked them for money, right? Anyway, the reason I'm bringing this up is because after lunch, Bill and his dad were to see the Antarctic NSF movie in a room with a giant screen. So I put 2 big chairs up there at lunchtime so that when they came in the room, they were sitting up front together. And the IT guy came into the room and he could not get Microsoft to boot up. And I just thought that this was very poignant. Bill's father actually looked at his son and went, we really need to fix this, Bill. I thought, this is my Microsoft moment. So anyway, Bill did read my book alley and wrote a nice little jacket, a blurb on it, so I was very happy about that. Now I also take people to Antarctica. I don't do this for profit. I do this because I believe that once you go to Antarctica, you become an ambassador to Antarctica, and you learn about climate change on this philanthropic cruise. I've taken 250 people now from Birmingham with me on this cruise that has 200 guests over the last 10 years. It's not inexpensive, but it's a wonderful, wonderful cruise. So if you have colleagues or people that are interested, just talk to me. It's sold out this January, but it's 21 it'll be going. Why is it important? Well, part of it is that we buy a piece of equipment that we give to scientists there, which is really nice. Climate scientists and people learn about that, and a lot of the folks come back and they talk to their congressmen and senators. It can be really important. I also am interested in how religion might be a vehicle for educating people about climate change, and how the care of creation in the biblical sense certainly has importance and relevance to climate change. And I've had workshops that I've helped run, and I've been the keynote speaker now for 2 very large annual faith community meetings by the Episcopal Church, and I'm working on the Southern Baptist. This year I became the face of the Nature Conservancy's National Can We Talk Climate Pledge. So this is an honor, and what it is essentially a pledge, not for a penny, but that you will, within 7 days of taking the pledge, talk to one other person about climate change. And then it has this wonderful website information about how to talk to Uncle Charlie, who thinks global warming is a hoax, and it's just fantastic. But we as Americans don't talk about it enough. We need to more. And then let me finish. So this was a great honor. This year, as a fellow of the Explorers Club, I won an award called the Finn Rohn Memorial Award for Antarctic Research, and for taking that research to a global audience. I had no idea when I won this award and went to the annual dinner where they have 2,000 people in this big auditorium, that I was going to share the stage with 8 living Apollo astronauts. This was absolutely stunning, particularly because my wife is a big fan of space, and we had dinner with 2 of the astronauts that went to the moon, and that was pretty awesome. But the poignant moment of the evening came at the end when each of the astronauts was asked to tell an anecdote that was something a little unique that nobody had ever heard before. And my favorite anecdote was when Mike Collins told Buzz Aldrin, this guy right here, a story that they both chuckled about. You see, Mike Collins, who was the guy that stayed on the vehicle and went around the moon, while Buzz Aldrin and Neil Armstrong went down to the moon, he just sat there for a couple days, right? Mike Collins did not like Buzz Aldrin. Buzz is kind of a pain. If you watch the movie Toy Story, you know that this character, Buzz Aldrin, is the character in that movie. He's just a little grumpy. I mean, he was a little grumpy to me. I mean, he's like that to everybody. So Mike had a list of things that he wanted Buzz to change in his behavior. And when the ship came off the surface of the moon to reconnect and go home, Mike turned down the request to reconnect. And he said, let me get my list. And he went down the list and made Buzz agree to all these various changes before they were allowed to reconnect and go back to Earth. So the real moment of the evening was not that, but when the last astronaut, there on the far right, Rusty Schweikert, who was the Apollo 9 pilot, stood up. Everybody else had sat. He stood up and looked at the crowd very seriously. He looked down the road at his colleagues and he said, you know what? All of us have been up in space. And all of us have looked back and seen this planet. And all of us here know how fragile it is and how much we need to take care of it.